This study introduces the work entitled The Impact of a High-Fat Diet on Liver Health in Pregnant Mice and Their Offspring. The role of the gut-liver axis, conducted by the research team of Shoupeng Fu and Wenjin at Jilin University College of Veterinary Medicine, published in iMetaOmics. The high-fat diet HFD, a prevalent modern dietary pattern, exerts systemic consequences that extend beyond initial assumptions. As the central metabolic organ, the liver becomes the primary target of HFD-induced pathology. During pregnancy, dramatic metabolic adaptations including estrogen surge and reduced insulin sensitivity potentially amplify HFD-induced hepatotoxicity. Pregnancy represents a critical developmental window where maternal nutrition directly impacts intergenerational health. Notably, while existing research emphasizes offspring metabolic abnormalities, a pivotal question remains unaddressed. Does maternal liver injury influence fetal hepatic development? Experimental validation is still required. The gut microbiota, often termed the hidden organ, demonstrates metabolic capabilities surpassing hepatic function. Through the gut-liver axis, microbial communities engage in intensive molecular crosstalk with the liver. How does gestational HFD modulate gut microbiota to influence maternal hepatic health? Can these microbial alterations transmit hepatic consequences to offspring? This study systematically addresses these knowledge gaps through integrated microbiota metabolome analysis, providing mechanistic insights for prenatal dietary guidelines. The accumulation of lipid droplets leads to lipid toxicity and the release of damage-associated molecular patterns, activating Kupffer cells and promoting inflammation. This pathological process was confirmed by hematoxylin and eosin Huijie staining. By utilizing UPGMA clustering trees and histograms, we observed that HFD induction significantly reduces the proportion of lactobacillus and helicobacter, while increasing the proportion of Murobacillacea and Blashia in the intestine. To gain a detailed understanding of gut microbes under HFD conditions, we plotted abundance histograms between marker groups. In terms of elevated flora in the gut, representative species include Blashia and Lachnoclostridium. Bile salts play a pivotal role in regulation of various hepatic metabolic processes, including bile acid synthesis, glucose metabolism, and lipid metabolism. To understand the impact of HFD during pregnancy, we used intestinal microbial metabolomics to examine the effects of intestinal microbial metabolites. Our study found that the alterations in gut microbiota and metabolite disorders interact, contributing to metabolic and inflammatory issues during pregnancy. In previous studies, we found that HFD causes significant alterations in intestinal metabolites, with LCA emerging as one of the most prominent metabolites. To investigate whether elevated levels of LCA contribute to liver inflammation in pregnant female mice, we administered LCA orally and monitored its effects on liver health. These outcomes further corroborate the presence of an ongoing inflammatory response in the liver, which is similar to that induced by HFD. As LCA has been shown to cause liver inflammation in pregnant mice, it is reasonable to assume that it may also impact the liver function of their offspring. Therefore, we evaluated the hepatic function and inflammatory indexes of the offspring mice to investigate this possibility. These observations suggest that high levels of LCA during pregnancy can have detrimental effects not only on the mother, but also on the offspring's liver health. In summary, our research strongly advises against prolonged high-fat diets during pregnancy, and suggests that modifying dietary components may improve liver health outcomes for both pregnant women and their children.